we're going to be digging into limits just a little bit more, looking at some limits of piecewise functions, limits of absolute value functions, and the squeeze theorem. So, we're going to start reviewing yesterday. If you look at this notation, it says the limit of f of x as x approaches a equals L. I don't know if you know what this symbol means, but it means if and only if the limit as we approach from the left equals L, and the limit if we approach from the right equals L. Just like we talked about yesterday, a two-sided limit exists if and only if both one-sided limit, meaning the left-hand limit and the right-hand limit, exist and are equal. So that was just a little review from yesterday. The limit from the left and the limit from the right need to be equal if there is a limit at that point, regardless of direction. Determining whether the limit as x approaches 4 f of x exists on a piecewise function. Let's start by sketching the graph. 8 minus 2x starts at 8, has a slope of negative 2, and notice they want us to go until 4, but less than 4, which is going to put an open circle at the 4. Those should be touching. It's not working right now. There we go. And radical x minus 4 means our radical function moved right 4, so it looks something like this. Now, those are rough. Does it appear from the graph that a limit will exist? Yes. And it appears that that limit will be at 0 because they're both approaching 0 from the right and from the left. Let's check algebraically. What is f of 4 in the first function? Because that would be the left-hand limit. Probably a better way I can write this. The limit as x approaches 4 from the left side would be of 8 minus 2x. Step 1 is solving a limit. Plug it in if that's possible, which it is, and we get 0. From the right-hand side, we get radical x minus 4 because that is the function on the right, which gives us radical 4 minus 4, which is 0. Is the limit from the left and the limit from the right equal? Yes, they are. Therefore, our limit as x approaches 4 of f of x is equal to 0. Keep in mind, at any point, you may pause the video to fill out the remainder of your notes. Let's talk about absolute value functions for a second. It's hard to decide because an absolute value function looks like a v. We could figure out what the numerator of this function looks like, but combined with the denominator would not be so easy. So let's start by drawing just the numerator. The absolute value of x minus 2 would be the absolute value moved right to. So it ends up looking like a v in that regard. If you think about it, absolute value functions are simply piecewise functions. Solve as a piecewise function, just like we did before, and graph it. So let's talk about this. X minus 2 really is a piecewise function. It looks like one function when x is less than 2, and another function when x is greater than 2. Because they're equal at that point, it doesn't really matter where we put the equal to bar. Just don't put both, or it is no longer a function. Would not pass the vertical line test. If you notice, the left-hand side of this graph, meaning this portion, its equation is negative x plus 2. Slope of negative 1, y-intercept of 2. To the right of that function, if we thought about this and had the graph continue, we would know that it was the function x minus 2, a slope of 1, a y-intercept of -2. So, here's how we can work through this situation. We need the limit as x approaches 2 from the negative side, and the limit as x approaches 2 from the positive side. The negative side, the x minus 2, is at the bottom on both. We're approaching from the left, that's going to be this negative x plus 2 function for our absolute value. If we're approaching from the right, that's just going to be x minus 2. Let's check this out a little more. Can we plug in our 2 in this first example? Can we plug this in here? No. We're going to get division by 0. So instead, we're going to do some algebra. Let's pull out our x minus 2. We're left with the limit as x approaches 2 from the negative side of -1, which equals -1. It's our constant rule, one of our limit laws from the previous video. This one already reduces. No, we can't plug the 2 in, but this easily simplifies to 1. And again, a constant is a 1. So, we know from the left side it equals -1. From the right, it equals 1. Therefore, our limit as x approaches 2, regardless of direction, of x minus 2 over x minus 2 does not exist. Because the limit exists from the left and it exists from the right, but they have to be equal for it to exist overall. Limit theorem 2, common sense theorem, although reading it may not feel that way. It says if f of x is less than or equal to g of x, which means f of x is below g of x, when x is near a, except possibly at a, then the limits of f and g both exist as x approaches a, and the limit of f of x as x approaches a is less than the limit of g of x as x approaches a. Let me sum this up for you. What this means, here's g of x, here's f of x. Notice that f of x is less than g of x everywhere, even at our a value. That means the limit of f of x at a and the limit at g of x of a is going to hold that same relationship. Your limit on f of x is going to be lower than your limit on g of x. In words that you can write, if a function is above another, then the limit at the same location will have the same relationship. Finally, the squeeze theorem, and everybody knows this as the squeeze theorem. So when we get to AP test questions and they ask you to justify your answer, if you know it's true based on the squeeze theorem, you can just say the squeeze theorem instead of having to describe what the squeeze theorem is. We'll get to more of that as we approach the text. But it says, if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, then if the limit of f of x equals the limit of h of x, notice they're equal and h is the highest and g is the lowest, or f is the lowest and g is between them, then g must also have that limit. Let me show you what I mean. We have a function h, call this h of x. Notice it's the biggest, but they tell us here that the limit between h and f are equal. So we know that f much what we are saying is if you know one function is above another, and the highest and the lowest are the same at a point, then you know g is the same at that point also. So, let's look at an example of that. It says, if 2x minus 1 is less than or equal to f of x is less than or equal to x squared for 0 is less than x is less than 3, find the limit of f of x as x approaches 1. So, we need to check. Our limit as we approach 1 of 2x minus 1 is going to be 2 times 1 minus 1, which is 1. Our limit as x approaches 1 of x squared is going to be plug in your 1 squared, which is 1. Notice, f of x is between 2x plus 1 and 2x minus 1. So, based on that knowledge, we know the limit as x approaches 1 of f of x has to be 1. We know f of x is always between 2x minus 1 and x squared between 0 and 3. 1 is between 0 and 3, so we know that 1 will be the limit of f of x as well. We know that because 2x minus 1 is less than or equal to f of x, which is less than or equal to x squared. On tonight. We'll talk about this more tomorrow. Come with questions.